In this and following videos, we're going to look at decimals for fractions, which are rational numbers. Today, we're going to look at the case where the fraction has finite decimal representation. In the case of 1 over n, where n is a positive integer, we want to prove that n does not contain any prime factor other than 2 and 5. Alright, so a few examples here where we have 1 over n is 128, that's 2's power, or 5th's power, right, 5th's power, and this is 5th's power. They all have finite decimal representation, right? We want to prove that n contain only factors 2 or 5. Okay, so we start from the fact that this representation is finite. So in the decimal, we're gonna have single digit d1, d2, and dk, where of course there are digits from 0 to 9. Of course, the final digit is non-zero. Yeah. So if that is the case, the right-hand side is actually a fraction where you can shift the digit here by dividing 10's power, right? So let's rewrite the equation here. So notation here is not repeating digit, but rather the integer composed of those individual digits, right? So m is some integer value. From this equation, you know that n and m multiplication would get 10 raised to k's power. So which means n contains only factor 2 and 5. Okay, so it cannot contain any other prime factor other than 2 and 5. That's the proof. Now, how about for the fraction that the numerator is not 1? Do we make the same conclusion? The answer is yes. So the same argument here, we assume m is smaller, and m and n are co-prime. Okay, so it's a finite digit here. By the prior argument, we have this. Now this time, we're gonna have the product equal 10's power times m. However, since n and m are relative prime, we're going to use one of the number theory basic theorem. That is, if two numbers are co-prime and n divides m times t, in this case, n has to divide t. Now, apply t to 10's k's power here in our case. We say that n and m are relative prime, so that means n has to divide 10 to the k's power. Yeah, so from there we conclude that n cannot contain any other prime factors. All right, so that's the proof. But what about the non-terminating case, right? So for example, this notation here, meaning the repeating decimal here, in this pattern is going to repeat. And there's another example with a shorter period length, and 49 is even longer one. Okay, this is 42 digits here. Now we can look at the period length for the case where the fraction has infinite many decimal digits and with repeating pattern. So what is the period length, right? So we're going to look at that in next video, and please subscribe to the channel to check out the follow-up videos on the subject.